All right, welcome back, Senior Math. Today we are discussing something a little bit different. We're still sticking with our probability and still sticking with our um, combinations, permutations a little bit, but we're going to look at something called binomial distribution today. So thinking back to the beginning of our statistics portion of this year, what was the difference between discrete and continuous variables? What was the difference between discrete and continuous variables? This was your warm-up that you had today. So thinking back at the very beginning of the year, we talked about how discrete represented numbers that were always whole numbers. They were your counting numbers, like 0, 1, 2, 3. These are your counting numbers. Like you have that specific amount. You can't have any decimals. We can't have anything else that was different. No rational or irrational numbers. While our continuous variables, these represented anything else. It could have been like 2.5 or pi or 3 minutes and 34 seconds. These are all examples of continuous variables. Now, continuous variables also includes 0, 1, 2, 3, so on and so forth. But they represented all of those other numbers that were not just your normal counting numbers. Any of those decimals, any numbers in between, any weird irrational numbers that we have like pi or e or I. And they also included like times in there. And so discrete versus continuous numbers told us two different things. So sometimes we worked with, sometimes when we are giving a survey question, sometimes we got continuous results as our answer. Sometimes we had discrete answers. For today's lesson, we are going to be working strictly with discrete numbers, and we can only do this with discrete numbers. So that's why it's important for us to know when is it discrete, when is it continuous, because in our situation, we have to be using discrete variables today. So that's one thing we'll remember. So we can only use those counting numbers. So there's a few types of scenarios that use discrete variables and probability that can be modeled using a formula or technique called distribution. So some certain scenarios or situations can be modeled or all have these same patterns that stick to them, and we call these patterns distributions. And so we will learn about two different types of discrete variable distributions, not this week, this and next week. I apologize for that. Not this week. Two types of discrete variable distributions and how to use something called distribution chart to help us solve for the probability of certain events and specific outcomes. So we're going to use this to help us find different events, so different probabilities using these distribution charts. So we have something called binomial distribution that we're going to talk about today. So binomial distribution is an experiment that can result in only two outcomes, such as a coin toss. You either get heads or you get tails, or a voter being in favor of a politician or not being in favor of a politician. It can any situation that always has two specific outcomes and only two outcomes can be modeled using binomial distribution. So, for example, a sociologist is interested in studying how many elementary teachers at a school are over the age of 45. You are either over the age of 45 or you're not. A soft drink marketer is interested in the proportion of Coca-Cola drinkers that prefer that brand. So you either prefer the brand or you don't prefer the brand. And then a geneticist is interested in the proportion of population who possess the gene linked to Alzheimer's disease. So you either have the gene or you don't have the gene. All these scenarios always have two results. It's either a yes, or it's either a success, or it's either a failure. So it's a yes or a no. So the word binomial, bi means two. So that first part of that word means two. So that's always going to tell you there's always going to be two results, either the yes or the no, or of whatever situation you're looking at. So that's why it's called binomial distribution. All right. So there's 5 specific characteristics that have to be considered for an experiment to be able to be considered binomial distribution or a binomial experiment. So we have to meet all 5 of these traits in order for it to be a binomial distribution. One, the experiment has to consist of n identical trials. So there has to be some number of identical trials. So, for example, if I'm surveying people, I'm surveying 1,000 people. Each one of those people is a different trial, but I'm giving them all the same identical question. That would be an n identical trials. Each trial must result in one of two outcomes. So we said it's binomial because it has two outcomes. You have either the success that whatever they answer is true, or whatever they answer is false or not true, or whatever. So you're either getting the yes or the no. They either like your brand or they don't like your brand. They either have the gene or they don't have your gene. It's that two possibilities. The probability of success on a single trial is equal to P and remains the same from trial to trial. So the probability of success is always going to stay the same no matter who you ask. So if I'm giving the survey of a yes or no question, the person's either going to say yes or they're going to say no. That probability is going to be 50%. If I do a coin toss, the probability that coin landing on heads is 50%. The probability that coin landing on tails is 50%. If I have a 30% chance of kicking a goal or like a soccer ball into a soccer goal, and I kick it like 100 times, I'm going to have a 30% chance of succeeding and a 70% chance of failing every single one of those times, assuming the situation is identical each time. So P is just going to represent the probability of each of those trials of success. So all the trials need to be independent of each other. So that means they do not affect each other once again. Independent means they don't affect each other. So every single trial has to be independent. So when I ask this person a survey question, it doesn't affect this person's survey question. When I flip this coin toss, it doesn't affect this coin toss. And we are interested in the probability of X, the number of successes observed. So we're always looking for what is the probability of this result happening. So what's the probability of 20 people saying yes, they prefer that brand? What's the probability of out of my 100 people, 30 say that no, they do not have this Alzheimer's gene? So we're always going to be looking for X, which is the number of successes. All right, suppose there are approximately 1 million adults in a country and an unknown amount are in favor of a politician having term limits. A sample of 1,000 adults is randomly selected from this population and asked whether he or she is in favor of the politician having term limits. The ultimate objective of this survey is to estimate the unknown proportion P of adults in favor of term limits. So is this a binomial experiment? So we just have to see, does it meet those 5 characteristics? So looking at characteristic number 1, the experiment consists of n identical trials. Well, we're asking 1,000 random adults. You're asking them, are they in favor of term limits or not? So we do have our n identical trials. So we meet number 1. Each trial results in one of 2 outcomes. So they're either in favor of the term limits or they're not in favor of the term limits. So yes, we do meet that outcome. The probability of success on a single trial is equal to P and remains the same from trial to trial. So we don't know what the probability is in this case, but we can assume that it's a 50% chance that ahead or yes in favor, or they're either going to be no in favor. Because this is just a random sample, it's randomly selected people. They're either going to say yes or they're going to say no. We don't necessarily know what that probability is, but it's going to be essentially the same per person because it's all random. And so we meet number 3. The trials are independent. Yes, it does not matter. If I ask this person what their answer is, it's not going to change what this person's answer is, assuming all those answers are conclusive. Everyone's filling out their own survey. Everything's fine. So that is independent. And then we are interested in the probability of X, the number of successes observed. Yes, we're looking for how many people are in favor of having term limits. So we're looking for what is that answer to X? How many people are in favor? What is the probability of this many people happening? So this would be considered a binomial situation because it meets all 5 of those characteristics. So big old yes right there. All right, so binomial distribution formula. So we have a formula to calculate binomial distribution. And here's our fun little formula that we get to use. I don't know why there's a dot there. All right, so our formula is the probability of X equaling some number. So the probability of our number of successes, which we said was X, equaling some number. So R is just some number. So the probability of X equaling some number is equal to N, which represents the total number of experiments. So how many people are you asking? How many cars are you looking at? Whatever your experiment is. So the total number of experiments, combination. So this, once again, that's one of our combination things that we just talked about. So it's N, your total number of experiments, combination, that same some number, whatever that number is, whatever number we're trying to see what X is, times P, which is your probability of success, which might be 50%, it might be 30%, it might be whatever, but it's just probability of success, raised to the power of R, which once again we said was some number, times Q, which is the probability of failure, probability of not being a success, raised to the power of your total number of experiments minus that sum number, whatever that sum number is, and that will always be given every problem, whatever that R is. So this is our probability. This is our binomial distribution formula. There's a lot going on here. There's a lot to take in. Now we could use this formula to help us solve for each thing. If I put in a number for R, if I had the total number of experiments. So in order for us to be able to solve this, we need to know three values. What is N? What is R? Not N again. What is R? And what is P? Those are the three values we need to know. Technically, we also need to figure out what is Q. But if we think about it, if there's only two options, there's success and failure. If you know what the probability of success is, you can just do 1 minus the probability of success, and that's going to give you your probability of failing. So those are the four things we kind of need to know, but we don't really necessarily need to know Q because we can solve for it. And then you plug this information into your formula, and you get a number. Now that's fun and all, but that's a lot of stuff to have to. This is a big formula to remember. So what some people have done is they have plugged in numbers for pretty much most of these results for all different types of numbers, and they put this thing into a chart. And they've compiled all this information into a chart. So all we have to do is look at this chart and look up the result, and then we can get our answer. So this is called our binomial distribution chart. And it's right here, and it's on Schoology. So it's your binomial distribution chart. So if we look on the left-hand side of your chart, these are your n's. So we have an n of 2, we have an n of 3, we have an n of 4, we have an n of 5, and it goes all the way down to an n of 20. So we have whatever your n is, goes all the way down. I think it skips a few numbers, but those numbers we shouldn't have to worry about. It also then has your r. So the r of 0, 1, 2, 0, 1, 2, 3, 0, 1, 2. So that r changes depending on what your n is. And then it has the p at the top. So you have your n on the left-hand side, the r on the left-hand side, and then the p is at the top. So we have like a p of 0.1, a p or 0.01, a 0.05, a 0.1, a 0.15, 0.25, and so on and so forth, all the way up to 0.95. So these go up by 5. So I shouldn't give you anything other than those going up by 5s. But those are your p's, your probabilities. We do not have to worry about q on here because once we find p. So people have used this formula to calculate all of those values, and then they've just compiled it here. So we can use this chart. If I know that n is 2 and my r is 2 and my probability is 10, I can just look, oh, my answer is going to be this one right here. And I have my result. And so we just need to use this chart. We just have to be able to find our values, look at the chart, find what the result is, and then write it down. So this will save us a lot of time so we don't have to use that formula right there. All right, so let's practice using this chart. So let's find so let's say the probability, get rid of that, the probability of x equaling 2 for the binomial random variable with n of 10 and p of 0.5. So here's our steps for what we have to do. First thing is so we have 2 is our r, we have a p of 0.1 and an n of 10. So those are our pieces. First thing we need to do is we need to find the n. So we need to find n equaling 10. So I'm going to pull up my chart, and I'm going to scroll down until I find n of 10. So n of 10 is right here. So this is my n of 10. So that's my first step. Moving on to step number 2. I need to find p of 0.1. So p of 0.1, looking over. Okay, yeah, I can't quite see it. But it goes 0.01, 0.05, 0.010. So p of 0.10 is going to be this row going up and down right here, or 0.1. And then I need to find r of 2. So r of 2 is right here. So this 0.194 is going to be my answer. So all I have to do is just look at the intersection of my n of 10, my r of 2, my p of 0.1, and that is my answer, 0.194 or 0.194. So p of x, the probability of x equaling 2 for this scenario is going to be 0.194, and that's how we use our probability distribution chart. So let's practice some examples of these. So I want to find, let x be the binomial random variable with an n, a p of 0.3. Find these three values. X is equal to 4, x is equal to 1, and x is less than or equal to 6. So we'll talk about how this one's different at the bottom. Let's start with this. So we know n is 7 and p is 0.3. So let's find those parts first of our table. So pulling up our chart, we need to find n of 7 and p of 0.3. So n is 7. So here's n of 7. Now my p is 0.3. P is 0.3 is going to be this row right here. So this row I know it's pulling all of them, but this row right here is going to be my P of 0.3. Now, next thing I need to look is, what is my R? So my R value for my first one is R of 4. So looking at my table, R of 4 meets with that line right here. So 0.097 is the probability of having n experiments with the probability of 0.3 being a success. The probability of 4 results being a success is going to be 0.097. Out of my 7 experiments with the probability of 0.3 being a success, the probability of just one of them being a success, exactly one of them being a success, is going to be 0.247. And now what this one is saying, this is saying what is the probability of x being less than or equal to 6? What is the probability of there being at least 6, or there's a probability at most being 6 successes? So I'm looking for what's the probability of any number less than 6 being my success. So what we have to do for this one is a little bit different, because I have to think what's the probability of any number being 6 or less for my success. Well, 0.04 is 6. That's less than or equal to 6. 0.025 is 5. That's less than or equal to 6. 4 is less than or equal to 6. 3 is less than or equal to 6. 2, and so on and so on and so on. So all of these numbers in this row right here, all these numbers combined are less than or equal to 6. Those are, I'm looking for all those probabilities. So what I can do in order to calculate this is, what I'm going to do is I'm going to take the probability of x being less than or equal to 6 is going to be 1 minus the probability of, so I guess there's two ways of calculating this. So essentially, what we can do is I just need to add up all of those values together. I just need to add up all of those values that I had together, and that would be my probability. We'll do it that way. So 0.3 is right here. So I'm going to take 0.247 plus 0.3181 plus 0.27 plus 0.297. I'm going to add all of these values up together. So pulling out our calculator, you will need a calculator for this. We'll just add all of those values together and we'll see what we get. So we get 0.082 plus 0.247 plus 0.381 plus 0.227 plus 0.0, oh, my thing is freaking out, 0.097 plus 0.2025 plus 0.004. These are all my values that are less than or equal to 6. I'm going to add all those values together, and I'm going to actually get a probability of 1. Now, how is this giving me a probability of 1? So we added all those values together, all those values equaled 1. Now, how did that give us a probability of 1? Well, if we think about this, adding all these numbers together, the only number that I didn't add together was this one right here, which was 0.001, which is this pretty much saying the probability of all 7 of those experiments turning out to be having a success, if the probability is 0.3 for each of them, and each of them being identical, is very, very, very small. So the probability of all of those being successes is unlikely. And so our probability of having at least one of those, or at least 6 being the most, is very, very likely. At least, or at most, there's only going to be 6 successes is very, very likely. And so another way we could have done this is we could have solved this by doing 1 minus the probability of x being greater than 6, which, well, if we have experiments of 7, the probability of x being greater than 6 is just the probability of x being 7, because that's the only number in our number of experiments that could be greater than 6, which we know this is 0.000. So it would be 1 minus 000, which is just 1. So essentially this is saying the probability of it not being this answer is so small that it's just too small for us to calculate, or that for us to worry about. We're not going to worry about any numbers that are too super small. So we're just going to say it's pretty much almost certain it's going to happen that we're going to have a probability less than 6. So let's look at some word questions of this while we move on. Let me check my time just to make sure I'm not running too far. Okay, I'm pushing it. All right, let's look at some word problems really quick so we can see some examples of this. Okay. Over a long period of time, it has been observed that the professional basketball player can make a free throw on a given trial with a probability of 0.8. Suppose he shoots 4 free throws. What is the probability that he would make exactly 2? All right, so from this information, we need to know our 3 things. We need to know, what is the N? How many experiments is he making? Well, he's making 4 free throws. So he's making 4. So we know N equals 4. We have to figure out what is the R. Well, we're looking for what is the probability that it makes exactly 2. So X equals 2. What's the probability that it makes exactly 2? And then we know P is 0.8. That's his probability of succeeding, 0.8. So we are going to go through N on our probability distribution chart. Look for N. We need to find 0.8 for our P, which is way over here. So I'll cover that up till I'm out. And then I know I'm looking for what is the probability that he makes exactly 2 of those. So I'm going to look for R equals 2. I'm going to go all the way over to my line. R equals 2 is 0.14154. So we're going to equal 0.154. And that's our probability. And that's how we can solve this. What is the probability that he will make at least 1? Probability that X will be greater than or equal to 1, at least 1, because we know 1 is going to be the smallest value. Well, if we think about this, probability of X being at least 1 is essentially, it's saying what's the probability that it's going to be any number. If we look at just this row over here, it's going to be the probability that any number bigger than 1. So the probability of X being this number, or plus this number, plus this number, plus this number, all these added together is going to be at least 1. So one way to easily calculate this is I can either add all of these numbers together, or I can do 1 minus my other number that I'm not subtracting, or I'm not adding together. So 1 minus the probability that X is less than 1, which is going to be the same as 1 minus the probability that X is 0. Well, what's the probability of X being 0? What's the probability of no free throws going in? Well, the probability of none of his free throws going in is going to be 0.002. So this is going to be equal to 1 minus 0.002. Now, I could solve this the exact same way that we solved the last problem, where I add up all of these numbers together. I could add up all those ones, and that would still give me the same answer. But I found this way just to be a little bit faster because there's only one number that I have to worry about. So 1 minus 0.002 is going to be 0.998. So the probability that he's going to make at least 1 free throw is very, very likely, almost certain. All right, let's look at this last question. Okay, so this is going to be our last question we're going to look at. I'm going to skip that next one. A home security system is designed to have a 99% reliability rate. Suppose that 9 homes that are equipped with this system experience attempts a burglary. Find the probability of these events. At least 1 alarm is triggered. So we have a 99% success reliability rate. So that means our P is going to be equal to 0.99. Suppose there are 9 homes that we are testing. So N equals 9. And then we're looking for what's the probability that at least 1 alarm is triggered. So probability that X is greater than or equal to 1. So once again, we're looking for the probability that at least 1 alarm is triggered. We can do the probability that it's 1 minus the probability of X is less than 1, which the probability of X being less than 1 is the same as 1 minus the probability of X equaling 0. So we just have to figure out what is the probability of X equals 0 and subtract that, because the probability of X being less than 1 is just, there's only one number that's less than 1 for our discrete numbers, because once again, we're not worrying about any decimals. We're just worrying about discrete numbers. So first, let's go to N equals 9 and P equals 0.9 or 0.99. Oh, this table doesn't have that. I messed up. All right, we're just going to pretend it's 0.95. I apologize. That's my fault. I forgot this table is different from my last one. All right, so let's look at N equals 9. And we're looking at this last row here. So the probability of it being 0, of X equaling 0, is 0.00. So that means it's almost so unlikely that we don't even need to calculate it. So we're doing 1 minus 0.000. So the probability of at least 1 alarm going off is going to be equal 1, because it's almost super certain that it's going to happen. So it's very, very likely it's going to happen. the probability of exactly 7 alarms being triggered. So the probability of X equaling 7. So once again, we just have to look for where's 7 on our table. Well, okay, so R equals 7 is this row down here. So we're going to bring this all the way over. So it's going to be 0.063 is a probability of exactly 7 alarms being triggered. So all 9 of these alarms having their alarms go off, the probability that 2 of them are going to fail essentially is 0.063. And then 8 or fewer alarms are triggered. So the probability that X is going to be less than 8 is the same as the saying as probability, or same as saying it's going to be 1, if I can write numbers, it's the same as saying 1 minus the probability of X being greater than 8. Well, what's the only number that we can be greater than 8 if we have 9 experiments? The only possible number we can be greater than would be probability of 1 minus probability of X equaling 9. So what's the probability of X equaling 9? What's the probability of all of them going off? Well, the probability of all of them going off is 0.630. So they have a very, very unlikely chance of failing. So they have a high chance of succeeding. So we're going to do 1 minus 0.630, and we'll subtract that. And that's the probability of at least 8 or fewer alarms have been triggered. So 1 minus 0.630 is 0.37. So there's a 40% chance, essentially, that of these 9 experiments, one of them may fail. There's a 40% chance that one of them may fail. But at least 8 of them, no matter what, at least 8 of them should succeed in total. So a probability of at least 8 of those alarms going off is 0.30. So this is our binomial distribution. Once again, it's really all using that chart. I apologize, I wasn't able to get to all of my questions. And so if you have any questions, especially about like the less thans or greater thans problems, let me know and I can help answer those better for you. We have a little bit of practice over this and you have an exit slip to finish out your day. Let me know if you have any questions. Have a great rest of the period.